All right, let's get right into it. Today, we're going to crack a code, the chemist's code to be exact. We're going to figure out why those molecule drawings you see everywhere, well, they aren't exactly telling you the whole truth.
Okay, I'm just going to come right out and say it. Those molecule drawings you've seen a million times, they're lies. I mean, they're useful lies for sure, but they're still not the real picture.
Yeah, those flat connect-the-dots things are just, well, they're a shortcut. The reality is that molecules are these incredible, complex 3D structures. Take L-DOPA, for instance. This thing is used to treat Parkinson's disease. Its shape is everything. And what's wild is that all these complex shapes are basically governed by one super simple rule.
And that rule is called VSEPR theory. Yeah, I know, the name is a total mouthful, but the idea behind it, it's beautiful. All it says is that the different parts of a molecule want to be as far away from each other as they can possibly get. That's it. That's the whole game.
Seriously, that's the whole thing. It all comes down to personal space. Just imagine all the different bits of a molecule elbowing each other, trying to get comfortable and not be all crowded. That's what's happening on a microscopic level, all the time. So let's see this in action. We're going to build up all the basic molecular shapes from scratch, just using this one simple idea of, giving everyone enough elbow room.
Okay, let's start with the easiest one. What if you have a central atom with just two other things attached to it?
A great example is acetylene. See how each carbon in the middle is only connected to two other atoms? So the big question is, how do those two groups get as far apart as they can?
Well, they form a perfectly straight line. It makes total sense, right? We call this linear, and the angle is a perfect 180 degrees. You literally cannot get any further apart than that.
Okay, easy enough. Let's level up. What happens when you have three groups attached to that central atom?
Look at ethylene. Each carbon there is surrounded by three things. Obviously, a straight line isn't going to work anymore. So, what do? They spread out into a perfect flat triangle. It's called trigonal planar, and those angles are all exactly 120 degrees. It's like a perfectly balanced peace sign.
And now for the big one. The most common setup you'll find, especially in organic chemistry. A central atom with four groups around it. Now, your first thought might be, oh, just make a square, with 90-degree angles. But wait, remember, molecules aren't flat. They live in a 3D world. So to really get away from each other, they don't form a flat square. They pop up into this amazing 3D shape called a tetrahedron.
And this is exactly why we have to think in 3D. In this tetrahedral shape, the angle is 109.5 degrees. That's way more space than the 90 degrees they'd get in a flat square. More personal space means more stability.
All right, so you've got the basics down. But every good story has a twist, right? So, what happens when some of those things that are pushing each other around are invisible? Check this out. It's a bit of a puzzle. On the left, we have methane with carbon in the middle. On the right, methylamine with nitrogen in the middle. Now, both of those central atoms have four groups around them. So why on earth do their shapes look so different? Okay, here's the big reveal. That nitrogen atom has an invisible group. It's called a lone pair of electrons. You can't see it like you can an atom, but it takes up just as much space. It's just as pushy. So the overall arrangement is still tetrahedral, but the shape we see, the one made by the atoms, looks like a little pyramid. We call that trigonal pyramidal.
And it gets even more interesting. Look at methanol. That oxygen in the middle also has four groups, but two of them are atoms, and two of them are these invisible lone pairs. And man, those two lone pairs are really pushy. They shove the atoms down and create this classic bent shape.
Okay, let's take a breath and put this all together. This little chart is basically our cheat sheet. See that total groups column? That tells you the starting point. If you have four total groups, it's always going to be based on that tetrahedral shape we talked about. But then the final shape we actually see all depends on how many of those groups are atoms and how many are those invisible pushy lone pairs. That right there is the secret to the whole thing. So now we get it. We know the 3D truth. But let's be real. Drawing every single atom and bond every single time would take forever. There's got to be a shortcut, right?
Oh, for sure. Just look at this drawing of cyclohexane. I mean, writing out all those C's and H's is a total pain. And worse, all that clutter actually makes it harder to see the important part, the actual shape of the molecule skeleton.
So chemists did what chemists do best. They came up with a code. It's a visual shorthand, a way to draw these huge, complicated things in just a few seconds.
Once you know the secret, of course.
And the rules are actually super simple. Rule 1, any corner or any end of a line, that's a carbon. Rule 2, just assume there are enough hydrogens on each carbon to give it 4 bonds. And Rule 3, if it's not a carbon or a hydrogen, you just draw it in. That's it. And with that code, that messy thing we saw before, it just becomes a nice, clean hexagon. So much better.
And there you have it. It's kind of mind-blowing, right? Everything from how a medicine works in your body to why a rose smells the way it does, it all comes down to the 3D shape of molecules. And all of that comes from one simple idea, personal space. So it makes you wonder, doesn't it? What else in our universe, from the tiniest particles to the biggest galaxies, is secretly being run by such simple, beautiful rules of geometry?